So it is my pleasure to introduce Professor Brian Logan. He is a professor of computing science at the University of Aberdeen. So I'm very happy to have him as a colleague and hope to collaborate with him in the future. He's also a visiting associate professor at Utrecht University and has an honorary position as a special professor at the University of Nottingham. His research interests span the specification, design, and implementation of autonomous intelligent systems. And he is a very well-known researcher in multi-agent systems. So it's my pleasure to welcome you, Brian, and put my mask back on. And we have a clicker over here for all of the presenters, so we are free to use it if you want. This one should move it forward. Yeah, the one should. The other one goes back. Yes, there you go.
Thank you. Well, I hope people won't mind if I take this off, because otherwise I don't think people at the back will be able to hear me. So first of all, thank you for the invitation to give this talk. It's a very interesting workshop, and I look forward to talking to many of you about the work that you're doing. I think it's a great initiative that you've started, so thank you. I think this talk will cover 3 of the 4 areas that Raphael was mentioning. There's a little bit of work in robotics. There's certainly some work in multi-agent systems, and most of it is about verification, or rather synthesis, as you can see from the title. So I should start with some acknowledgements. This is joint work with Natasha, who is here, and 2 of the organizers of the workshop, which may sort of explain partly why I was invited to give this talk. Thanks to Louise and Angelo for letting me talk about this work, but it's also part of a bigger strand of work which hasn't looked at fail-safe behaviors, but in which we've looked at synthesis of control programs for autonomous systems and robotic cyber-physical systems. And that's with Thomas Brastil, Giuseppe Giacomo, Paolo Felli, and Moshe Vardi. So most of this talk is going to be about motivation and the setting, and trying to convince you that this is an interesting problem. There will be a theorem at the end, but it's going to be quite light on technical details. I'm happy to talk about the technical details if people would like to, maybe in the coffee break, or if you have questions, but mostly it's about the motivation and the setting. So as you probably know, given that you're here at this workshop, writing software for autonomous systems is hard. And for many safety critical applications, the software that we write has to be verified. We need to be able to give some guarantees that the behavior of the system is at least safe. Now, one thing that can happen when we verify software is that we discover some bugs, and hopefully the counterexample from the model checker will help us to understand what the bug might be. And so we revise the software, and then we re-verify, and we go around the loop. And we repeat until we get software which is safe. So this is quite time consuming. So another way of doing it is to actually synthesize the software for an autonomous system directly from the specification of the system. The safety property, for example, that we would like the system to adhere to, or some reachability property, some goal that we would like the system to actually achieve. And that's what this talk is about. So reactive synthesis techniques have been proposed as a way of doing synthesis of control software for cyber-physical systems. And the strand of work that I was talking about, this larger strand of work, has largely been in that area, where we looked at synthesizing controllers for, among other things, manufacturing assembly plants, where you want to build a product and you want to be able to guarantee that the product will be built correctly. So in this kind of setting, we're given a description of a description of the autonomous system, which I'm going to call resources, is some sort of generic term for the robots and other things that we are going to be using, maybe machine tools or guided vehicles, things like that. And a high-level specification of the task to be performed, of the tasks to be performed, which I'm going to call the target. So we want to automatically synthesize a controller for the autonomous system, the resources, to perform the task. And the nice thing about this is that because of the way we do it, the controller is provably correct by construction. So we're basically just taking model checking, running it in reverse, starting with the specification and outputting a control program in order to meet the specification. So here's a little example to try and make this a bit more concrete, and it's in the setting of transducers. So we're modeling both the resources and the target as automata with output. I'll come back to transducers a little bit later. So, but the key idea here is that we want to synthesize a controller which at each step delegates the input output from the target. So the target is a transducer which is telling us what we would like to happen at the next step. And what the controller is doing is deciding which of these resources is going to respond to this particular input and where the outputs from that transducer are going to go. Maybe they go to a different transducer, maybe we make multiple steps here in order to realize one step in the target over here. And we do this in such a way as to simulate the target transducer. So we want to be able to mimic all the steps that the target transducer might be able to make using these available resources. So a couple of applications of this kind of technique, some stuff that we did before in Nottingham, which is autonomous manufacturing, where the target is a product, or actually a product family that we want to be able to manufacture. We want to be able to manufacture all variations of a particular type of product that might be specified at runtime, so the color, the finish, all these sorts of things, using manufacturing robots and other machine tools. Another application, which is to work with Louise and Angelo and Natasha, was looking at autonomous inspection and maintenance, specifically for fusion power plants. So again, this is a more obviously safety critical application, but these things are very dangerous if you get in their way. They can easily knock a person over. So that's the idea. Now, for most of the rest of the talk, I want to explain to you why this idea has a problem and what the potential solution to that problem might be. So I said the controller, if we synthesize it in this way, is correct by construction. And that's true, but it comes with a kind of caveat. And the caveat is that the correctness of the controller relies on the assumption that the models of the resources and the specification of the target behavior are themselves correct. Now, you might think that they clearly would be correct, but if the target behavior is itself unsafe, so the person who specified the target didn't think through all the consequences of what they're asking the autonomous system to do, then maybe the autonomous system will do something that in broader context is not what we want. Or if some of the resource operations are unsafe or incorrectly programmed, so maybe the robot has a malfunction, maybe the person who wrote the low-level control software for the robot didn't anticipate some motions that you ask it to do, or the resource models don't include all possible failure modes that you might think of, then synthesis can result in a correct but unsafe controller. So it's provably correct with respect to the assumptions we make, but the assumptions themselves are maybe violated in this case. And this is something which is increasingly of interest to people, as the fail-safe control of autonomous systems is being investigated in things like the draft standard for fail-safe design of autonomous and semi-autonomous systems. There's sort of IEEE working group that's looking at these sorts of things. So people are starting to think about, well, what happens if things don't go the way that we expect them to go? So what I want to spend the rest of the talk on is what I'm going to call a fail-safe controller, where we have some additional information, which I'll try and make precise in a moment, about how the system is behaving in the world and how we might want to respond to things that don't appear to be going as they should be. So a fail-safe controller fail-safe controller orchestrates the available resources in such a way as to achieve the target, just as before. But in addition, it also guarantees the resulting behavior conforms to a fail-safe specification. Now, this is a separate specification of behavior, which I'll talk a bit more about in a moment. But briefly, what the fail-safe specification does is it defines how the target behavior should be modified when an abnormal event, that is one which goes outside the assumptions which we've made when we were specifying the resources and the target behavior actually happens. So these are things like resource failures, a human entering a robot cell when humans are not supposed to be in a robot cell, the fire alarm going off in a manufacturing plant, things like this that the designer of, say, specifying a product to be manufactured as a target behavior would never think of what to do if the fire alarm goes off. You know, it's not part of their problem. They're thinking about what to do if the customer wants it red, not how we shut the whole system down. So abnormal events can be generated by sensors. So if we have sensors on the resources themselves, or maybe we have a camera with some basic vision processing capabilities that can determine that the human has walked into the cell. So we can get events which indicate that something is happening that is abnormal. It's not what we would expect in the normal run of the system. Or if we need patterns of events over time, then we can use runtime monitoring in order to get signals when things are not going the way we would expect them to go. And what I mean by appropriate behavior or appropriate response to an abnormal event, it differs depending on what the event is. It might be, if it's a fire alarm, for example, it might be to shut the system down. If it's a human has walked into a robot cell and it's safe to do so, then we can just pause the robots until the human or if it's something else, if the robot hasn't moved to the correct position that we commanded it to, and we can tell this perhaps through feedback from a camera, then we could perform some remedial action. So for example, we could try recalibrating the robot arm to see if that fixes the problem and allows us to continue. So I'm trying to present here a relatively flexible framework. It's a way of thinking about what happens when things don't go the way that we would actually like them to go. Now, for people who are familiar with synthesis or generating controllers for these sorts of things, you may be thinking, well, what you're talking about is just the product of the fail-safe specification and the actual target. But it's actually a little bit more complicated than that, because we don't want to carry on trying to produce the target if something abnormal happens. So basically what we're trying to do here is to synthesize a controller with two modes. One mode, which is for normal operation, when things are going the way we would expect them to go. And one mode is for handling abnormal events, including how to return to normal operation, if that's possible, after the abnormal event is over. And these take precedence over these. So if something unexpected is happening, then we want to do this rather than the standard behavior. So just the other reason for thinking of these two things as separate is that the target behavior may be realized using different resources, especially in a manufacturing context. The person who is specifying how a product is going to be made may not even know which manufacturing facility is going to make it. So the specification is done at quite a high level, and the actual implementation realization depends on the resources that we have. So the fail-safe specification, on the other hand, is specific to the set of available resources and should hold for any target behavior realized by those resources. So if a human walks into robot cell in a manufacturing plant, we want to pause the robots no matter what kind of product we're making. It doesn't matter. It's independent of the target. And also, different resources may have different fail-safe specifications for the same target. So if it turns out we're manufacturing our product in a manufacturing facility where the robot cells have safety screens, then we actually don't need to worry about a human entering the cell because it's just physically impossible for that to happen. So I'll briefly cover the approach and then give a little bit more detail as to how to do it. So the basic idea is to extend the work that we did before on using, which is based on transducers and synthesizing controllers from this representation of the resources and the target in terms of transducers. So we model both the target behavior and the available resources as multi-port transducers. So they're a transducer with multiple input and multiple output ports. So these take an infinite sequence of tuples of symbols or events as input and produce an infinite sequence of tuples of symbols as outputs. So the input events are things like a manufacturing operation and the part to which the manufacturing operation is to be applied. And the output events correspond to the record of the fact that the manufacturing operation has actually been applied. So just to make this a little bit more precise, so the resources are modeled as non-deterministic multi-transducers, multi-port transducers. So for those of you who are familiar with transducers, this probably looks very familiar. We have an alphabet. I'm assuming here for simplicity that the alphabet of inputs and outputs is the same. We have a set of states. We have the initial state of the transducer. And because it's non-deterministic, the transition is specified by a relation. So the R says that in state S, with an input, a set of a tuple of inputs A, we transition to state S prime and output a tuple of an L tuple actually of outputs B. So that's a setting. Here's an example. So this is a extension of the manufacturing work that we did before. This is a very simple assembly robot that can place parts and attach them to a larger assembly. And the only figure is almost certainly too small to read from, especially from the back of the room. But the only thing I want to highlight here is that some of the transitions, like this one and this one here, are non-deterministic. So if we're asked to place an object, if the robot is asked to place an object, then the place can succeed, which takes us to state S1, or the place can fail. And in that case, we output a different signal from the signal that we output here to say that the place succeeded successfully. And that signal could be generated either by a sensor on the robot or an external sensor, which is watching whether the thing has been placed correctly. So what this non-determinism is doing here is it's modeling the anticipated failure modes of the resource. So these are things that we believe can happen. They happen so commonly that we build our model on the assumption that we need to be able to do something about it. And what the fail-safe specification is really talking about is the unanticipated failure modes and other things that can go wrong with the resource. The target is modeled as a deterministic multi-transducer. So it's just the same as the previous definition, except here the transition relation is actually a function. And here's a very simple example target transducer that simply attaches a part to another part using which can be realized by a couple of the robots of the sort that I showed on the previous slide. So I'll just skip over these fairly quickly since I'm conscious of time. Now, the more interesting thing perhaps is the fail-safe specification, but this is again modeled as a deterministic multi-transducer. So the fail-safe specification is for a set of resources. and it's just a deterministic multi-transducer, and we make the assumption that the alphabets of the resources that this is a specification for, and this alphabet of the fail-safe specification are aligned. We can obviously define mappings if we need to, but again, this just keeps things simple. So here is example fail-safe specification. Again, I'm not going to really go into the diagram. I think what is I want to get across, however, is the different kinds of fail-safe behavior that we might want to specify. So, for example, if a human enters a cell, the resource transducers representing each robot should output a stop symbol, indicating that the robots have paused. They're no longer moving, and hopefully that means there's no danger to the human in the cell. If there is a fire alarm, then each robot should output a power off symbol, meaning that somehow the robots have been put into a state which is safe to power them down. So if they're holding anything heavy, that may mean that they have to perform several steps to get into a state where we can actually power them off. If the human enters the cell and the alarm sounds, then the latter takes precedence. So we have to specify, if there are multiple abnormal events happening at the same time, what it is we want to happen. And when the human leaves the cell, then the robots can move again, unless there is an alarm. So if it was possible to do so, then we can carry on manufacturing the product or doing the maintenance operation or whatever it is the humans were doing. So we put these bits together, and the key, we get a fail-safe target, which defines the required behavior in both normal operation and when an abnormal event occurs. So the fail-safe target is just a pair consisting of the actual target behavior that we want to realize, if it's possible to do so, and the fail-safe specification. And the input to the fail-safe target is just a big tuple where the first set of elements are what the target is producing. And so the first K positions it corresponds to the target, and the last set of positions is the abnormal events that may occur. And we assume that one or the other happens. So abnormal events take precedence over normal inputs. So either the first set of inputs or the last set of inputs corresponding to the abnormal events are padded with epsilons, depending on whether things are running normally or whether something bad has just happened. And the output, again, is a sequence of length L plus M, corresponding to either the output of the target or the output of the fail-safe specification, again, padded with epsilons just to make things come out at the correct line. Okay, so we need, just a couple more slides. So we need to think about what to do after the abnormal event. So how can we resume operation? So as I said, abnormal events take priority over trying to perform the target behavior. So if we do get an abnormal event, we have at least two options. One is we should resume the target behavior at the point it was interrupted, or should we restart it with an empty history? And that may depend on things like whether we had to put things down that the robots were holding. And then we have to go back to the beginning of the target and say, actually, well, pick up the part again, and then go and attach it to the assembly that you were going to attach it to. So we assume that any sequence of abnormal events that we get terminates with a special marker, if it terminates at all. If the sequence of abnormal events just carries on, so for example, the fire alarm just keeps sounding, then we just continue with the fail-safe specification, we leave the system shut down. But if it is possible to resume, we either get a VR signal indicating that the target should resume from where it left off, or a VS signal indicating that it should be restarted from the beginning with an empty history. So since F can effectively change the state of the target because it can rewind it back to the initial state, the behavior of the fail-safe target is again simply not the product of the target and the fail-safe behavior. So I'll just skip over the next couple of slides. This is how the actual fail-safe controller is synthesized. So we may need to connect several resources together in order to achieve the steps in the target, or even to achieve the steps in the fail-safe specification, because these are high-level things. And the key idea here is a port binding, which specifies which output ports are attached to which input ports of other transducers. And there are some constraints that you might expect. So the set of port bindings must be consistent with a set of binding constraints, so that, for example, a physical output port can be bound only to one physical input port. So if we've made a part, we can only send it to one place. A part can't suddenly be in two places at once. And the port bindings, the other key thing to get across here is that the port bindings can be changed while the resources are operating. So the controller is basically deciding what the port bindings are. And it's moving signals or actual parts through the system by controlling the port bindings. So we now get an orchestration problem where we want to synthesize a fail-safe controller. And a fail-safe controller for a fail-safe target and a set of resources is a strategy which simply maps from the inputs to a set of bindings. So for each step in the combined inputs of the fail-safe controller, we have to choose a port binding, an appropriate port binding for the whole system. So the orchestration problem is then, is there a controller for the given set of resources and the fail-safe specification? We can show that the orchestration problem for a set of multi-transducers is decidable, and it's in 2x time, as you might expect. So just to wrap up, so I think this is just the beginning of this sort of work in this area. And the reason we started this is because, as far as I'm aware anyway, all the previous work in AI behavior synthesis that has looked at failures has assumed that the right thing to do on a failure is to restart the target, is to continue with the target. And that, I think, is not always the correct thing to do. It's not necessarily the safe thing to do. And for the reasons that I gave, I don't think it's reasonable for the person who's specifying the target behavior to know all the details of what should happen when things go wrong. So we've shown how to synthesize fail-safe controllers, which will achieve the target if possible. And if not, then at least we'll guarantee that the overall behavior of the system is safe. And I think this is a more flexible way of doing it. So that's the end of this talk. Thank you.
Do we have any questions?
Yeah. Thank you. This is very interesting. It kind of reminds me of Rumsfeld's known unknowns versus unknown unknowns. But unlike the unknown unknowns, you still assume you have symbols for describing these unexpected faults, right?
Yeah.
So, what happens if something you would never even imagine, like in a worldwide pandemic? How do you handle that?
We don't. Is the short answer. The longer answer is that you plan for the set of things that you think. I mean, if a meteorite strikes the factory, you probably have other things to worry about than whether you safely turned off the robots. So, as in giving any kind of safety guarantee, there comes a point at which you have to say, well, yeah, the little green men from Mars might arrive, but we're not really going to worry about that.
I had some addition to make
Hmm.
that for simplicity, Brian skipped translation, but the idea is that the resources understand some very simple things like they did shut down, and there is some kind of translation that when we get an event, the alphabet which is sent to the resources is translated into understandable things.
Yes, thank you. I was trying to fit a 50-minute talk into a 25-minute slot.
Any other questions?
I'd like to ask a question if I may.
Person.
Okay, thank you very much, Brian, for a very interesting presentation, very neat idea. I wonder if you have thought about the impact that such an approach would have if you're considering on-the-fly planning, adaptation of systems as things go wrong, or do you envisage this is for static planning? What's your view there?
Yes, we have. It's very interesting. Thank you. It's a very interesting question. I have two answers to the question. One of them is that yes, you can use the fail-safe specification to place bounds on the way in which an adaptive, self-adaptive, or learning system can learn. So if it starts to do things that you think it shouldn't do, then the fail-safe specification will cause the system to do whatever is safe. And in that sense, it's, thank you, it's behaving a little bit like a shield. If you're familiar with work on using shields in machine learning, reinforcement learning, where you have an automaton which specifies basically what the agent is allowed to learn, or more generally, which actions it's allowed to perform. I think there's quite a close correspondence between this kind of approach and the work that people have been doing in shields.
Thank you.
Okay, Bruno?
So I have a question. I'm not really in the field, but so you go into this phase when you have something unexpected that arrives, and then you try to make it better, and then if you manage, then you go into this normal mode. So is it not possible that, for example, if the pandemic is going for a long time, there's something in the fail-safe that says, oh, actually now consider this as normal, and then
yes, you could do that. You could have, I suppose you could have some kind of layered fail-safe specification that says, okay, for the first 5 minutes, try to recover. Try to recalibrate the robot. If recalibrating the robot doesn't work, then you can shut it down. We actually have an example of that in the work that I was showing, but you could nest the layers further so that if you wanted to have, maybe for something like an autonomous spacecraft or something like that, it might make sense that where it's not possible that humans can intervene, you might want to have some kind of graded safety fail-safe specification that tries to preserve as much of the capability as possible while maintaining the sort of the attitude of the spacecraft and other things.
We have time for one more quick question. I have one. So I'll take it off for a second. So as the name implies, fail-safe is considering safety aspects. Have you ever thought about trying to consider performance compliant behaviors such as agile robotics, or trying to maintain the behavior, a set of performance bounds to make sure that the controller is behaving good?
No, we have, but we haven't actually solved the problem. In the manufacturing work, we abstract away from a lot of things. So for example, the work that this was based on, we assume discrete model of time, everything moves forward in single ticks. That's a very big abstraction for a manufacturing setting. And the manufacturing engineers that we were working with were concerned about things like, well, this resource, this manufacturing resource, is no longer producing things at the same rate or speed or something that it was, and therefore we want to take some kind of corrective action, maybe switch to preferentially using another resource or something, because although it's possible to maintain the quality by some rework, it's clear that this machine is drifting out of alignment or something like that. So there was some separate work in the project that funded some of the earlier work on this, but the two were never integrated. But it is a very, I think, relevant, necessary thing that.
The reason I mention it is because there is this competition called ARIAC from NIST, the US National Institute of Standards and Technologies, and it's more worried about agile robotics. But recently, because Angela and I will be collaborating with them, we are trying to push them to add some safety metrics as well. So it could be an interesting scenario for experimenting some of those things. Yeah, I'd like to thank Brian again.